Suis-moi, là où je sais sourd, suis-moi.
In mathematics, green theorem gives the relationship between a line integral around a simple closed curve C and a double integral over the plane region D bounded by C. And it used only for vector field in two dimensions. This is a property of conservative or path-independent vector field, which form the basis for the Gaussian theorem for line integral.
From this clip video, we simplify about the green theorem. Green theorem is the one-to-one relationship that between area and circumference. It means that when you draw the closed path on any surface, the area inside the path can calculate by information of the path with respect the fixed point of area. From the formula, double integral equal to the half of closed path multiplied by x dy plus y dx. It means the area is equal to the small rectangle surface. When you know about the working area, you can calculate it. From the example you can see from video, you can see the two colors of circular is the green and the red circular. The center of red circular is mean the reference point, which we can calculate state from state, and the other one is the green circular is represent the point of circumference. By when you move the one of red circular on somewhere, you can put it on anywhere because it's not important, and move the green circular at the corner of the shape you want to calculate, and move the other green one on another corner. It can make you see the rectangular, and when you move the one of green circular on the clockwise, it will show the red rectangular. It means the positive area. In the other hand, if you move the green one on the counterclockwise, it will show the green area. That means the negative area. The area is changed by initial point, but the total area will unchanged. And this is all of clip video.
1. Green theorem is a generalization of the fundamental theorem of calculus and a special case of Stokes theorem. 2. Green theorem is in the proof of the Cauchy theorem. 3. The Green theorem is the parameter.
Je suis pas, suis-moi, là où je suis beau.
In this section, we will take a look at theorem that is the higher dimensional version of green theorem. This is Stokes theorem. We are going to relate a line integral to a surface integral. Let S be an orange smooth surface that is bounded by a simple, closed, and smooth boundary curve C with positive orientation, and also let vector F be a vector field. And then we will get the formula for find work in 3 dimensions of a closed curve. And note that the surface S can usually be any surface so long as the boundary curve is given by C. This is something that can be used to our advantage to simplify the surface integral on occasion.
Welcome to Stokes theorem. The idea of Stokes theorem is similar to Green theorem. However, in Stokes theorem, R becomes a surface S in space under the purple condition. Condition to apply Stokes theorem: the vector field N must point the same direction as your right thumb as your right finger curl and point in the direction of the path of the boundary C. This is called a positive orientation. Stokes theorem: if S is an orient surface with unit normal vector N with a smooth closed boundary C with a positive orientation, and F equal function f g h with f g and h have continuous partial derivative, then integrate f dot dr equal to double integrate gradient cos f dot n ds equal to double integrate curl f dot n ds. This is a flux integral. The line integral around the boundary equals the flux of the curl.
Application of Stokes theorem. Important applications Stokes theorem, sometimes combined with Gauss' law, provide a powerful tool for working with various sorts of surface and line integral. It has important physical applications.
Suis-moi, on y est ou presque. Suis-moi, là où rien ne presse. Suis-moi.
The introduction of divergence theorem. The divergence theorem is a theorem in vector calculus of the physical fact. The divergence theorem is an equality relationship between surface integral and volume integral, with the divergence of a vector field involved. It will use to solve some problem like mechanics problems. The equality is valuable because integrals often arise that are difficult to evaluate in one form, volume and surface, but are easier to evaluate in the other form, surface and volume. Thank you.
Let's see the river and we create the vector inside the river that represent the flow in of the water. So water flowing really quickly, then the vector belong. In this case, we want to really peaceful common river. So the vector will be the same length and the same direction. Nothing about what happened. I didn't know, just add pumping water into rivers. Downstream with a better, more river flowing. So we have the vector belonging represent a greater flow rate. Now imagine we have vacuum that sucks up water from rivers. Now downstream with expect to be less water flowing. So we have the vector be shorter. Divergence is the way that guide how particular point in a vector field in a source or a sink for vector. So here I have a host that would be a positive divergence for the vector field. Where is a vacuum that's a negative divergence? Here, the divergence is zero because it's not changing the amount of water. In general, if we see vector spinning out of the divergence for a point, or we see being strongest after passing through a point, then that point works like a source or a host, and so it's a positive divergence. On the other hand, if we vector tend to converge of a point, or they're weaker by passing through a point, then the point is like a sink or vacuum and is a negative divergence. If a point space does not subtract order the vector, then the divergence is zero.
Application of divergence theorem are the differential form and integral form of physical laws. As a result of the divergence theorem, a host of physical laws can be written in both differential form, where one quantity is a divergence of another, and integral form, where the flux of one quantity through a closed surface is equal to another quantity. Three examples are: first, Gauss' law in electrostatics; second, Gauss' law for magnetism; and the last is Gauss' law for gravity. Thank you.
Et v'là que nous y voilà. Ta-da-di-dou-dou. On se pose, c'est si bon quand on se pose.